So, I want to talk about what I find most interesting these days in complexity theory, which is sort of a tongue-in-cheek title. I call it experimental complexity theory. If you know anything about complexity theory, you realize that, 10 or so years ago, this would have been an oxymoron, right? There would have been essentially no connection whatsoever between experiment and complexity theory. And yet I think it says a lot about where we've come as a field that, I think in the last 10 or so years, this is now what I think is some of the most interesting questions, which are questions that are maybe not directly relevant to experiment yet, but are at least sort of motivated by questions that that naturally occur in near-term experiments. Okay, so let me. Okay, cool. So the starting point for this talk, and I think we all know this, that we've now seen the first quantum advantage claims. So we're sort of living in this really exciting time where there's at least a sort of plausible claim that could be made that near-term quantum experiments are doing something that can't be described classically, can't be solved efficiently on a classical computer. And we've seen this, several times now. First, famously, of course, by Google in late 2019, who implemented their so-called random quantum circuit sampling proposal in 53 superconducting qubits, and at a larger scale, a similar experiment by USTC in 2021. And then, there's also this sort of separate platform for quantum advantage on a linear optics architecture, which is called Gaussian boson sampling. It was first implemented by USTC in late 2020, and then more recently at a larger scale by a team at Xanadu. And so, in this talk, I want to tell you about the latest complexity theoretic arguments, the latest sort of very formal, provable arguments to believe, or to understand, or to characterize the computational power of these so-called random quantum circuit experiments. And it's a little bit confusing, even though the Google experiment, the sort of superconducting setup, is actually explicitly called random circuit sampling. Actually, in reality, these are both random circuit experiments. Okay. Okay, so now that's great, but who cares? Why do I care so much about this topic? What does it tell us? Well, I think there's sort of a computer science point of view and there's a physics point of view. I think from the computer science point of view, the importance of experimental quantum advantage it really extends to the very foundations of computation. It really amounts to asking, what does computation even mean? Right? It's almost philosophical. It's because we can think about it as the first experimental violation of the so-called extended Church-Turing thesis. And what this violation would mean is that if our goal is to model efficient computation by some universal theoretical model, we must consider quantum mechanics. That's really profound, right? What it's saying is that the model that served us well as computer science community for almost 100 years, right? The Turing machine, right? It's not the right model of computation. It's not the right model of computation because there are physical problems that can be solved in the real world that can't be solved efficiently on a classical Turing machine, right? And so this really has a sort of a seismic effect on what we think about, in terms of the foundations of computation. It's saying, we were not modeling computation correctly, right? So it's really, from a computer science perspective, I think completely obvious that this is really, really profound. But of course, it's not the first time we've said this as a community. Since the early 90s, we as sort of theoretical computer scientists have understood that at least in theory, quantum computers violate this extended Church-Turing thesis. But these early results like Bernstein-Vazirani in '93, Simon, and of course Shor, these were purely theoretical results. No one was implementing Shor's algorithm at a large scale. In the '90s, they're still not implementing Shor's algorithm sufficiently large scale to do anything that's super classical. And so the new thing is that we're really trying to have an experimental violation, right? To see an actual experiment that's solving a problem that couldn't be solved in a reasonable amount of time on a classical computer. So that's the goal. I think though it's also very interesting from a physics point of view. I think of the importance of experimental advantage as sort of validating quantum physics in what I think is sort of a new regime. Exponential growth of the Hilbert space. The fact that if you give me an n-qubit quantum state, that in principle I'd have to to write it down, I'd have to specify 2 to the n parameters, right? It's really, we sort of take it for granted when we work in quantum computing or quantum mechanics, but it's actually quite counterintuitive, right? It's so counterintuitive that I would say, that again, for the last 100 years, since people have been thinking about quantum mechanics, they've asked essentially the same question from different perspectives, okay? And that perspective, that question has boiled down to the same thing, which is this exponential description of a quantum state really necessary, or is it somehow a figment of our ignorance that, someday we'll wake up, we'll find that there's a polynomial-sized description, and we'll all be sort of much happier and go on our way. And so I think that's exactly what we're trying to figure out in Quantum Advantage. We're trying to really explore this new limit in which to test physics. Just like there's sort of high-energy physics, that sort of tests physics in certain regimes. I think we have a very similar limit in which to test quantum mechanics, which I call the regime of high complexity. When n is getting the system size is getting very, very large, and 2 to the n is absolutely enormous, sort of mind-bogglingly enormous. But in this sort of new regime, this high complexity regime, there's these really profound questions that come precisely because the system size is so large, right? Which is, how do I even know that I've done this, right? If I have an experiment, that's somehow manipulating, a Hilbert space of dimension 2 to the 53. It's mind-bogglingly large. How can I classically verify something that's sort of intrinsically exponentially complex, right? It's a really, really tricky question. It's something that we still don't know the answer to. But I think thinking about quantum advantage, right, experimental quantum advantage, it's really sort of spurred on development in this area where we're starting to think about how can we verify something that's so large, right? With a classical computer in a reasonable amount of time. I think before this, you didn't hear these discussions. Yeah.
Would you consider things like lattice QCD an example of computing the?
No, I wouldn't actually, and that has to do with controllability, right, and programmability, right. But we'll talk about this in more detail later. Exactly what we mean. Okay. Okay. So what are we trying to do? Well, I think the ideal goal is quite simple to describe. It's sort of hard to achieve, but simple to describe. We want a problem that has sort of 3 characteristics. Okay, we want to find a problem that, one, can be solved efficiently using a near-term quantum experiment. So we're not happy with things like Shor's algorithm because, Shor's algorithm is efficient in principle, but you need fault-tolerant quantum computer and so on. So, that's not near-term. You also want it to be classically hard to solve. And generally speaking here, we adopt the standard complexity theoretic notion of what this means, which is that, it's really important to get this straight, that the problem cannot be solved in a polynomial amount of time with a classical computer as the system size scales. Right? So this is really important. Complexity theorists don't generally talk about finite size systems and the hardness of simulating, a system at a particular finite size. Instead, they're interested in asymptotics and in scaling. They say as the system size grows, as n grows, what is the time it takes for the best algorithm to simulate this n-qubit system? Right, so this is a very different question. We're thinking about scaling here. And then 3, we want to demand that the solution can be efficiently verified with a classical computer with minimal trust in the experiment. And we're sort of obsessed with this as computer scientists, this 3rd point. It's really important that we can sort of check this problem, classically. And the reason is if we're thinking about quantum advantage as a test of quantum mechanics, right? We don't want to be in this strange situation where we're sort of assuming something about quantum mechanics, maybe something about the noise model of the system, right? To then test quantum mechanics. It's pretty obviously circular, okay? So it's very important to us that we take a very, very particularly stringent notion of what we mean to verify the system, that we're not making too many experimental assumptions, because otherwise you start to run into these pretty obvious circularities in having to do with what your goal is. Okay. Okay. Now, like so many things in life, there's the ideal goal. And it's very simple to state, and then there's the actual goal. There's the thing that we may be in danger of accomplishing. Okay. Now, there's a huge gap. An absolutely enormous gap, and I think it's really important that we're all really honest about this, okay? So let me actually call this the current goal, and we can sort of talk about the difference between the ideal goal and the current goal. So what are we doing? Well, current quantum advantage experiments, all of them actually, all the ones I described, solve essentially the same. The idea theoretically is very similar. They solve what we call sampling problems. In other words, the goal is to sample from a complicated distribution that's intrinsically specified by a description of the quantum experiment, like the quantum circuit. Okay, this is actually, we take this for granted these days because, all of these experiments, they're doing this, but it's actually not obvious at all that this is the right thing to do, right? In particular, complexity theorists, we generally don't talk about sampling problems. When we talk about complexity theory, like P, NP, all of these complexity classes, which are groups of problems, these are all groups of decision problems. We call them languages. That means, you have some input, X, and given X, the answer is yes or no. That's what a decision problem is. So when you talk about, NP or P, it's the class of decision problems, right, that you can solve with a computer that has certain resources, right? Maybe it takes polynomial time or is non-deterministic polynomial time like NP. That's not actually what we're talking about here, right? What we're talking about is a very different sort of problem where we're given an input. Generally speaking, the input is the description of some quantum experiment, like a quantum circuit. And then the goal based on that input is to sample from some complicated distribution that's specified by that input. Okay? It's a very, very different thing. It has certain advantages and certain disadvantages, but it's worth pointing out that that's what we're doing. Now, what we're going to focus on today, in fact, is that one upside to thinking about sampling problems rather than decision problems is that we actually have very strong, rigorous evidence, comparably strong evidence, I would say, that these problems, these sampling problems, cannot be solved classically in polynomial time. Evidence that, while imperfect, is much, much stronger than we can say about almost any other sort of computational problem. Okay, so that's going to be our focus. But what I want to say, and I think the biggest gap between sort of the ideal goal and what's actually going on, is that these current experiments are not scalable. And it's not just that they're implemented at 53 qubits and not n qubits. That's true, of course, but that would always be true for a real-world experiment. It's also that there's sort of two really fundamental issues that we have not figured out as a community, sort of how to solve with these experiments. And the first is that they require exponential amount of classical time to verify. Okay, so in fact, the way we're verifying them, and I'm going to be really clear about this, is essentially as complex as solving them in the first place. Okay. We don't know how to get over that. It's a major, major open question. It seems to be inherited from the sort of intrinsic difficulty of the switch to sampling problems. Sampling problems are sort of much, much more difficult in general to verify than decision problems. And two, which I think is also neglected, remember we're talking about near-term quantum experiments. So fundamentally, we want to incorporate the effects of uncorrected noise, right? We don't want to think about fault tolerance because that's not near-term. Sort of by definition, that's how I'm defining near-term. And so, if you think about uncorrected noise, well, it's going to get worse and worse as the system size scales if you're not making your gate error rate, proportionately smaller. Right? And so what you see, and I hope I can talk about this in more detail sort of later in the talk, what you see with any sort of reasonable sort of noise model in a near-term quantum experiment, it doesn't play very well with asymptotics. Right? If you sort of take your system size to infinity, which is generally speaking what we do in complexity theory, that's the name of the game. That's what we argue about. And you keep your noise the same, right? You end up with crap. Right? It's not something that's particularly difficult, and nor would we really expect it to be. So I think this is really, really important to realize that this is a giant issue where the theory is all about asymptotics, right? But but in reality that's not what we're doing. Okay? It's a big gap. Give me 1 second. So what I say is, in fact, when I think about near-term quantum advantage. The really important thing to realize is that our hope is really what I call to find a Goldilocks system size. So if you know Goldilocks, the fairy tale, you understand what I'm talking about. If you don't, I'll tell you very quickly. So Goldilocks is a little girl. She goes into the woods. She meets her friends, the 3 bears. And for whatever reason, the moral of the story ends up being that we should always agree with the middle bear. Okay, and so that's what you need to know. So what we're looking for is a system size that achieves this Goldilocks status. Namely, it's large enough to be classically challenging to simulate, right? Because if it's too small, then you can do it in your calculator, your classical computer, very simply. But it can't be too large, and I think this is what's often neglected in discussions like this. If it's too large, we will simply not be able to verify our signal. Okay, we don't know how to do that. And if it's too large, our signal will be too small. The signal-to-noise ratio will simply overwhelm us. Okay? And so NISQ advantage is all about Goldilocks system size, which in some sense means that complexity theory can never be, you know, the sort of the only thing that we argue about when we talk about near-term quantum advantage. Okay? There's more to it than that. Okay, now, what I want to say is this, sort of a relatively optimistic statement, which is there is optimism that current experiments have reached this size, okay, this Goldilocks size, but, you know, but classical simulation algorithms continually improve, as do quantum experiments, okay? So this is not something that we should think of as, you know, sort of a one-time line in the sand that we cross and then we're done. Rather, I see this as kind of a continual competition between the experiments, which are getting better, right? The system size is increasing. We hope the gate error rates are, you know, also going down. But, you know, the classical simulation algorithms are also getting better, okay? And I think maybe the reason I really wanted to talk about this you know, today is because I want to emphasize that much is still unknown, right? I get asked all the time, like, have we seen quantum advantage yet? You know, we see these crazy articles in the news, even very reputable news sources, and they say incredibly polarized things, right? On the one hand, you see people who say, oh, you know, we've solved a problem that takes 10,000 years to solve with a classical computer, and we've solved it now on a quantum experiment. That's not true, okay? It's just not true. We also see the other side, right? There's some new classical simulation algorithm, and you know, quantum advantage doesn't exist. That's not true. I often tell people, if anyone is giving you a summary about quantum advantage in a single sentence, they have to be wrong, right? And that's actually the accurate thing. We don't know, and I think it's really important to be talking about something like this in a winter school, precisely because I think the next generation is going to have to think about a lot of these issues and sort of try to push forward the frontier of this research, which leaves a lot to be desired right now. Okay. Okay, good. Let me have a last slide before I get into the math and proofs and so on, which is just what do we mean by random circuit? So what does Google mean by random circuit? Okay, and we'll end with that and take questions, and then go into the technical stuff. So what they mean is the following: they generate a quantum circuit, which we'll inevitably call C, on n qubits on a 2D lattice with d layers. We think of d as some parameter, which generally scales with n, of Har-random nearest neighbor gates. So each layer might look a little bit like this. If you see my really rough picture here, the circles are qubits. The edges are Har-random 2-qubit nearest neighbor gates. Okay. This might be the first layer. The second layer could be different. For example, maybe the horizontal neighbors, you know, the gates could act on horizontal neighbors rather than vertical neighbors, right? But the point is we start with some easy to prepare state, like the all zero state on all of our n qubits. We apply, you know, d of these, you know, d different gates, right? And then we measure all n qubits in the computational basis, and we get our sample, right? That's it. That's the problem. It's random circuit sampling. Implement a random circuit, certain depth, certain system size. You measure all n qubits, you get your sample. That's all it is. Okay, it's been implemented with n equal 53 qubits and d equal 20 by Google in 2019. This is a really famous demonstration, I think made like the front page of the New York Times at some point. And more recently by USTC with 60 qubits and depth 24. Okay, and this is going to be the focus of today's talk, but the analysis I'm going to tell you about is actually much more broad. It applies to a whole bunch of different experiments. So for example, I also talked about in the beginning, I talked in passing about these sort of bosonic experiments, boson sampling experiments done by USTC and Xanadu and so on. And in fact, much of the analysis is like directly applicable to those experiments too. Okay, so while I'm going to talk about random circuits, Almost all of the sort of random near-term experiments that are being done, quantum advantage experiments, can be cast in very similar language. Okay? Okay, great. So what are we going to do? Two things. I'm going to talk about the complexity theoretic hardness of sampling arguments. These are sort of saying, at least in principle, if we don't consider the effects of noise, right? Why are random quantum circuits hard to simulate classically? That's not obvious at all, right? In fact, the media will ask me this, like, what are they doing? And I say, well, random circuits, it's sort of like implementing random quantum code. That's all they're doing. It's like the classical equivalent is you have some distribution over lines of code. You then sample from that distribution. You get a random program and you run it. But why on earth should that be hard? Okay, that's going to be the focus of the first part of the talk. It's not obvious at all, even if you don't consider noise, which we're not going to, at least at this point. Okay. And then I want to talk about something a little bit more practical, which is the hardness of benchmarks. So these are other ways we can argue about the hardness of these experiments that more closely matches what's actually being done by the experiment. Okay? So first section, complexity theoretic. It's very idealized, but answers the question, why is there a hard to simulate quantum signal at all, even if in random circuits, even if we implement things perfectly? Second part of the talk, what do they actually do? Okay? Let me take questions. I think I had a few. I'd be kind of upset if there weren't questions at this point. Yeah?
You mentioned how it's difficult to verify in the quantum setting, but there's classical sampling problems where it's easy to verify.
Yeah.
I say okay.
Yeah, definitely. So to be clear, I'm not saying, maybe I should be really careful. I'm not saying that every distributional problem, sampling problem, is necessarily hard to sample from, to verify. Right? That's not the case. There are examples, but in general, it makes things more difficult for us. And when I give you the examples of the distributions we'll think about in the analysis, it should be kind of clear why it's going to be very, very difficult. Yeah.
So you said that as we increase the size of the quantum computer, it's difficult to verify.
Yes.
So what's the threshold? Till how many number of qubits can we verify?
Good. And that depends very much on the on what algorithm you're using, right? On what sort of random experiment are you talking about, and so on. But fundamentally, what we end up doing, and I'll talk about this more in detail when we get there, we actually end up doing we actually simulate these quantum circuits. We compute output probabilities with a classical supercomputer. Using sort of modern day sort of tensor network classical simulation methods on these the Google sorts of circuits, we can get to slightly smaller system sizes than were actually implemented. Like maybe if Google was implementing 53, you can do something in the 40s, something like that. And then we use some sort of extrapolation method to try to make sure that the data we see at 53 is consistent with the actual data that we've computed at 40, something like that. By the way, I'm a theorist, so when I use these actual numbers, you take them with a grain of salt, but it's something like 40. Okay? Let's see, other questions? Yeah.
So on the Goldilocks, So you mentioned that as you increase system size, the error increases, and that increases your ability to verify.
Yeah. No, these are really two. Okay, yes, they're sort of conflated. I think about these as two issues. So even if you didn't have noise, right, verifying would be a hard problem with the current experiments. There's separately though, when we talk about why we're looking for Goldilocks solution instead of just bigger the better, right? There's a separate issue, which is that we have noise, which means that unless we're sort of proportionally shrinking our system our gate error rate as our system grows, we're going to get our signal is actually going to exponentially decrease, right? Almost any sort of noise model you can possibly imagine has this property, right? You don't change your gate error rate, and you increase your size of the system, the fidelity, right, of your quantum state that you're implementing goes down exponentially, right? That means that almost by definition, we have to be really, really careful how large our system size we're actually implementing, right? Every time we grow our system size, we have to make the error better and better and better and better, okay? That's really, really important to realize. So often when you see claims like, okay, for noisy RCS, if there's noise involved, it's sort of easier to simulate than we might have expected. Those are interesting claims, of course, but that's not the same thing as saying that we've simulated the actual system, because we're not, we're generally not working in that setting when we think about quantum advantage, right? We're not working in the setting where, we're going off, our system size is going to infinity, and we're not proportionally shrinking our gate error rate. So the real question to be asking is this practical question, which is that at the exact system size that the experiment was done, say 53 qubits with the same gate error rate, how hard is the best classical algorithm? How much human time? Does the wall clock time? Does the best classical algorithm take to simulate it? Right? Yeah.
So Google claimed to have achieved quantum supremacy.
Yeah.
Whatever. Is that just not true? Is that claim not true, or is it just depends how you?
Yeah. Right. This is sort of what I've been talking about the whole time. It depends on a number of things. It depends what you mean, right? If what you mean is infinitely scalable quantum advantage that it can be verified efficiently so that we can be completely sure that the quantum signal is really there with the classical computer running in polynomial time, Google absolutely did not do that. In fact, I'm very comfortable standing here today and telling we're not even close to that. Like, I've never even seen any experiment even claim to do something like that, right? If, on the other hand, the question is there a plausible reason that at the particular system size Google implemented and at the error rate that they actually had, right, that the quantum computer solved this problem, this random circuit sampling problem, in less wall time, you know what I mean by that, right, human time, than really sophisticated classical supercomputers, right? Then we can debate about it, okay? I think probably at 53 qubits, what Google was doing, that can be simulated in maybe a matter of hours with really sophisticated tensor network methods. But then the USTC experiment, which is 60 qubits and slightly deeper, right? Then that's at the moment that we don't know how to simulate that in even a reasonable amount of time, as far as I can see. But again, this is a race, right? The algorithms get better, they get more sophisticated, they use more structure of the system than we knew could be exploited before, right? And the experiments get better. The noise gets better, the system size gets larger. It's not a line in the sand. Yeah? Sorry, someone else had a question. Yes?
So you rightly point out that as you scale a quantum computer, the errors get worse.
Right.
Any real scaling of a quantum computer is going to require a hierarchical error model, which translates into
of course,
mitigating errors at different scales.
Exactly.
Error correction being the best known of those. How do you include that into a real analysis of the scaling of algorithms running on computers like that? Or is this like beyond where we're
okay, no, it's not beyond where we are. I mean, okay, sorry. We don't know how to do it, that's the answer. We're working on it, right? But that's very much the sorts of questions that we're asking because we've been talking about these sorts of systems, right? What is the realistic way of talking about these sort of hierarchical models? It's not actually obvious at all. Precisely. And in fact, I think so much of why I think it's really exciting to be thinking about these things now is because we're starting to ask these questions in a rigorous setting. Right? I'm actually not aware of people asking these questions before. Right? I think it's very fashionable to think about sort of near-term algorithms and just sort of act like noise doesn't exist, and then later on say something really vague like, oh yeah, but then the circuit depth of my quantum algorithm was really shallow. We all know that really shallow quantum circuits, they don't decohere very quickly. But that's actually not completely true. Right? There's some truth to that, but it's not the full statement. I think quantum advantage is really, making us take these things very, very seriously, very rigorously. And so I think you'll hear some of that as well later. Can I? Yeah. Yeah, please. Yeah.
Have there been any use case of this sampling task?
Yeah, that's a great question. So that's not actually what I put in my definition. So I didn't have solving a useful problem as part of the definition. But I'd be lying if I said we weren't thinking about that really hard. So one thing that we've been thinking about recently is how to, which I think doesn't get as much press as it should, actually, is how to use random circuits to, like what Google has been doing, to solve cryptographic problems. So in particular, to certifiably generate random numbers, right? So to come up with a random number whose randomness can actually be proven to a skeptic who doesn't believe that the hardware is working correctly or doesn't believe in quantum mechanics. We think that's the sort of application. So like Scott Aronson has a famous proposal about this, and we've been working on that as well. We have a follow-up paper.
Would that require the same amount of classical computing resources?
Yes. Now, in some of those applications, that might be okay. right? But not always. And they're certainly not scalable applications for the same reason that random circuits are not scalable. Yeah? Good. They're not truly random. They're pseudo-random. And the theory doesn't actually require that they're truly random. Yeah, that's a great question. We'll talk about that. Yeah. I think I love the questions. Maybe we should keep going, but maybe one more? No? Yeah, one more.
I did not understand what exactly random circuit sampling is.
What? You didn't understand the definition. Yeah, let's go back. So, I think I have this. It's all in this very, very simple picture, right? You choose, okay, at a high level, you choose a random circuit. That means the gates are random, what we call Haar random, just like the uniform distribution for continuous objects, right? And you pick this circuit randomly, you apply the circuit to some really easy input state, like all zeros. You measure all n qubits at the end of the day on the standard basis. You get out your sample. That's it. That's the problem.
But can you verify, like you don't know what the gates you applied and you get.
You do know the gates. You do know the gates. You're holding the gates in your hand. You pick a circuit randomly. It doesn't mean that you don't have the gates. The circuit now is fixed. It's random but fixed, right? I'm holding that in my hand. In principle, on my supercomputer, I can compute the output probabilities of that circuit. In fact, that's what they do to check it. Not all the output probabilities, a small number of them. It's an exponentially hard problem, as we'll talk about in a moment, but that's actually what happens. I'm going to keep going, but these are great questions. Thanks. Okay. So let's go now to the theory. So my goal now is to convince you that sampling is from a quantum circuit, even a fixed quantum circuit, not necessarily a random quantum circuit, is a hard problem in principle. Not obvious at all. It's not clear why that should be. It doesn't look anything like something that before this we thought was good on a quantum computer, like factoring or something like this, right? Okay, so like I said, current quantum advantage experiments sample from the output distribution of a given quantum circuit. It's a mathematically rigorous problem, right? We're given as input the classical description of a quantum circuit C. So that means, literally the classical bit string that specifies the gates of the circuit. Then we ask the experiment to run C on all zeros and then measure all n qubits to get a sample Y, which is an n-bit string. That's the problem. Okay? Sometimes we take C to be random, sometimes we don't, depending on the analysis we're thinking about. Okay? That's the problem. So let me define something. We'll call the output probability of the circuit this Py of C. I'm just going to use this throughout this convention, throughout the entire talk. Just the probability that if I start on all zeros, apply my circuit C, measure all n qubits, I get Y. That's very simple, right? Okay, what's the first goal? Well, we're not even going to talk about random circuits for the moment. What we want to do is we want to prove the impossibility of an efficient classical sampler algorithm, which I'll call S. S is supposed to sort of simulate a quantum circuit, okay? Which in a very strong sense, which we want S, this classical algorithm, to sample from exactly the same distribution as the quantum circuit would sample from, okay? So let's now rigorously say what we mean. So we mean for all circuits C and outcomes Y, we have that, if I look at S, that's a classical sampler algorithm, right? S for sampler. It takes as input the circuit, because that specifies the distribution, and then it also takes some random coin flips, okay? And the guarantee at the end of the day that we want to make about S is that the probability over the choice of random coin flips are that the outcome of this sampler is equal to Y is equal to the quantum probability, the Py of C. Okay? And our first goal is to show that such an algorithm cannot exist. Okay? That's the goal. Yeah?
So, you introduced the coin, but the coin definitely helps.
Absolutely. In fact, this argument, in the end, maybe I'll ask you if I forget. It's a great question. If I can't do this, if I can't sort of think about the algorithm as like pulling out the randomness, that's what we're doing here. S is deterministic, right? And it depends on, random coin flips. If you can't do that, the argument won't work, and that's good because, that's exactly what we can't do quantumly, and yet we can sample from that distribution. So that's precisely the reason the quantum algorithm will not also trigger the same hardness consequences. because you can't pull out the randomness. For a classical algorithm, this is actually, you can always do this. And this is a basic theorem. You can always think about a randomized classical algorithm as a deterministic algorithm that takes as input random coin flips. Okay, great. Okay, now, how are we going to analyze this? We want to prove that no classical sampler algorithm S exists. And how are we going to do this? It's actually very, very simple. Oh, yeah? Efficient, absolutely. We're complexity theorists, it's going to be really important that it's efficient. Okay, now, how are we going to analyze this? Well, actually, the starting point is really, really simple. I'm going to introduce two problems that are very simple to describe. They're very hard problems computationally, but they're very simple to describe. I'm going to call them the classical sum problem and the quantum sum problem. Okay? Quantum sum, by the way, has nothing directly to do with quantum mechanics. I'm just trying to be kind of provocative. Okay? So here's the classical sum problem. We're given a classical circuit, that's the input, that computes a Boolean function f, which I want to think of as taking n input bits and spitting out 0, 1. It's just a sort of standard Boolean function. And then our goal is to compute the sum over all inputs x, right, of f of x. Okay? It's the classical sum problem. By the way, why do I want this? The only thing that's a little tricky here is why do I want the input to be a classical circuit? Any ideas? Why would I say that? Why would the complexity theorists always do this trick? Why would we do that? Sorry? Yeah, you want to evaluate it, sure, but the real reason I have in mind is that if I just said given as input f, right? Well, it could be that the input is actually the truth table, in which case the length of the input is really 2 to the n. Okay, I don't want that to be the case. I want the length of the input to be polynomial in little n, the number of variables. So that's why I make this distinction. There's no other reason, okay? Cool. How hard is this, by the way? We know this? There's P, there's NP, there's other stuff. How hard? Any ideas? Yeah. I mean, there's no polynomial time algorithm for sure, if that's what you mean. It's sharp P, yeah. So let's think about it. Complexity theory is all about SAT, the SAT problem, right? So I give you a Boolean formula. Let's call it psi. It's not a wave function. It's a Boolean formula, right? Psi. And now I ask, how hard is it to know if psi has a satisfying assignment, right? What is that? That is NP, that's NP complete, thank you. Okay, awesome, right? That's of course just asking if this sum is greater than 0, right? Because, right, if f was a Boolean function, right? A Boolean formula, like a 3-sat formula, right? Then computing the sum over all x would simply be saying, and asking if it's greater than 0 would simply be equivalent to saying, is there a satisfying assignment or not? Right? Okay, but now we're doing something even harder than that, right? Because we're actually computing the sum. And as was pointed out correctly, this is something called sharp P, right? It's the hardness of computing the number of satisfying assignments to a Boolean formula, right? Because that's exactly what this sum is telling us. If f was a Boolean formula, 3-sat formula, psi, then sum of x, psi of x is nothing more than counting the number of satisfying assignments. Right? So this is a very, very hard problem. Okay, but it gets harder. So here we go. I'm gonna make a very simple change. I'm gonna call this the quantum sum problem. Again, provocatively, because it's not really quantum. We're going to again be given a classical circuit that computes a function, but I'm just gonna make one change, and that's it. So now it's plus minus 1 valued instead of 0, 1 valued. It's the only difference. Okay? Now I ask exactly the same question. How hard is it to compute this function? Okay. What do we think? Is it about the same difficulty, right? Well, the answer is it depends. Okay? If the goal is to compute exactly the sum, in fact, it's essentially the same difficulty. All you've really done here is relabeled the outputs, right? It's not so interesting. Okay, but so what I'd say is for now, let's talk about exact computing. Well, then they're both sharp P hard to compute. So they're both at least as hard as computing the number of satisfying assignments of a Boolean formula. The second guy, since we're talking about exactly computing it, It's really just relabeling the outcome. It's just a sort of, not very important, not very interesting, actually. Yeah? It's going to get more interesting in a moment. So we're going to consider approximations. So we're going to sort of consider weakening the problem. So first, this classical problem. We're going to relax it a little bit. I'm going to call this the classical approximate sum problem. So the input is exactly the same. It's a circuit that computes a Boolean formula. But now, rather than computing exactly the sum over all inputs of x of f of x, I want to say how hard is computing what I call a multiplicative estimate to this sum, right? So it's just an alpha that's between 1 minus epsilon times the value of the sum and 1 plus epsilon times the value of the sum. Okay? So this is just a relaxed version. It's easier than the exact problem because you don't have to output exactly the sum. And here's the thing, and I'm not going to prove this, but it's a very famous theorem in complexity theory. Sometimes we call this Stockmeyer's theorem. And it's actually, in some ways, I think it's commonsensical. It's saying the following. Roughly speaking, what it's saying is it's strictly easier, unless nasty things happen in the complexity world, which we can't prove, but we don't believe. This approximate problem is strictly easier than the exact problem. Okay? The way we formalize that, which is not super important for us, but it's that it turns out this problem, Stockmeyer's algorithm says that this problem can be solved in polynomial n and 1 over epsilon time with an NP oracle. If you know what an NP oracle is, that's great. If you don't, it doesn't really matter. The point is we don't think that sharp p-hard problems can be solved in with this amount of resources. So even though it uses an NP oracle, and so it's not efficient, strictly speaking, it's not something that you can simulate on your classical computer on your desk, it's still not enough resources to solve this sharp p-hard problem. So the important thing is this classical approximate sum we believe to be strictly easier than the exact classical sum problem. Okay, that's the important part. Okay, let me give you the consequence, the way we're going to use this, okay, which is the following. Suppose a classical sampler algorithm S exists. That's the algorithm we were talking about before that takes a quantum circuit and a random string and so on, right? Well then, assuming that something like that exists, then outputting a multiplicative estimate of the probability of any outcome that sampler outputs y, that's strictly easier than the exact counting problem, the exact classical problem. Why is that? Any ideas? How do I see that? Well, I'm going to show that this problem, namely if a classical sampler exists, right, then computing the output probability that sampler outputs any given outcome y, that's an n-bit string, right, that's a classical classical sum problem. Where do I see that?
You have to sum over everything and divide by.
Yeah, exactly, precisely. And sum over r's, right? Yeah, exactly. So why is that? That's exactly what he said. Let's define the following Boolean function. It's a 0-1 Boolean. It's a classical Boolean function. It's going to be a function on the random coin flips, the r. And we're going to say that it's 1 if the sampler on input r is equal to y. That's our outcome that we care about. And otherwise 0. Okay, now, by definition, because it's a sampler, right, the probability that it's a classical sampler, the probability that this sampler is equal to y can be written in terms of this sum, right, over something small, right, over the number of random strings. That's this 2 to the length of r, right? But now that's generally exponentially small because we think of that r as like a polynomial length string. Why don't I care? That's sort of interesting, right? Why don't I care? That's an exponentially small quantity. Usually I'd really care about that because that means this is, if it was just this, right, just the sum, then it would clearly be the, the counting problem. But it's not. It's this over some normalization. But I don't care. From the perspective of approximation, I don't care. Why? Yes, but what is important about it? It's multiplicative, right? The point is that the way we've defined approximation is multiplicative, so even if the quantity itself is really tiny, the error is getting proportionately small. And that's the point, okay? So anyway, if you understood that, that's great. If you didn't, the important thing is that if a classical sampler exists, then outputting a multiplicative estimate to the probability that that sampler outputs any given outcome, we believe to be strictly easier than sharp P. That's the important thing. That's the take-home message. It's take-home message because it's going to be very different when we consider the quantum approximate sum problem, which is exactly the same thing, but with the only difference being we now map to plus minus 1 rather than 0, 1. The notion of approximation is exactly the same. Okay, it's multiplicative approximation. Here's what I'm going to claim. This problem, unlike the classical problem, is as hard as computing the sum exactly. Okay, we're going to prove this, or at least sketch a proof, because I think it's quite surprising. It's really the heart of all quantum advantage experiments has to do with this dichotomy, the fact that one of these sums is harder to approximate than the other. But I want to ask, first of all, any ideas why there might be this discrepancy? Like, what on earth is going on? I relabeled things. And, when we considered exact sums, it didn't matter, right? But approximation seems to matter. What on earth could be happening? Yeah. Exactly. So, precisely. So why might I have called it quantum? It's actually, the answer is the same. Oops. What quantum phenomenon does this maybe vaguely resemble? Interference, right? That's the point. It's an intuition. It's not it's not super rigorous, but that's what I wanted to sort of draw your attention to. Okay, cool. Really large cancellations in this problem seem to make it a lot harder. Okay, but we're doing math here, so we're going to prove something. So let's prove this. A computer scientist would say that the proof that if I can solve this approximate problem, I can solve the exact problem. Computer scientists would say it's a binary search and padding argument. Okay, what does that mean? So it means the following. Well, first, let me just make my job a little easier. It's not super important, but it makes my job easier. So I'm going to claim that even computing the sign, spelled S-I-G-N, so whether it's positive or negative, that even this is sharp P hard. Okay. Now that suffices to show that the approximate sum problem is sharp P hard. Why? Because multiplicative approximations preserve the sign, right? So so it's an easier problem to compute the sign than to compute the multiplicative approximation. All right, so this is what I'm going to show. I'm going to show that if I can compute the sign of some x g of x for any function g that maps 0, 1 to the n to plus minus 1, I can use that to compute the sum exactly. Okay, that's my goal. And how are we going to do this? So this is the padding part of the binary search and padding. Well, the first thing to realize is, what's the setting? You give me a function g. You say, okay, Bill, you compute the sum over all x of g of x. I don't know how to do that, okay? But let's assume I have the ability to compute the sign of the sum for any g. Okay, I happen to have a box in my hand that does that. How am I going to use that box to compute the sum? Well, first thing I notice is I'm not stuck with this function alone. I can sort of manipulate it a little bit to change what that sum is, and that's what's going to be called padding. Okay? So what do I mean? By adding dummy variables, okay, so more variables, right? Maybe g has n variables, and let's say I'll add, k other variables or l other variables, whatever. I can manipulate the value of that sum essentially as much as I like. Okay? What do I mean by that? Let me give you an example. So let's say the goal is to compute the sum of x sum of x g of x for a specific g that's on n variables. Now I'm going to construct a new function. I'll call it g prime. It's also plus minus 1 value, but it's on n plus 1 variable. So it's on one additional Boolean variable. And the way I'm going to program that function is really simple. I'm going to look at the last bit, that n plus 1th bit that I added. Okay? If it's 0, okay, I'm just going to run g, the original function, on the first n bits and output whatever g outputs. Okay? If the last bit, that n plus first bit is 1, what do? Output 1 or minus 1, but something constant. Right? Now what did I just do? What did I just do? I'm not doing binary search yet. I will, of course. That's where it's going. But it's exactly this, right? What I've done This is, I guess, if I was padding by -1, the output would be -1. What I've done is, okay, I don't know what the sum x g of x is. I don't know what the sum and this is x prime because it's over more variables, of g prime of x prime. But what I know is the relationship between the two. I've shifted things, okay? In particular, the new sum of this new padded function is equal to the old sum minus k, for whatever k I like, depending on how many variables I add and so on. And now I think basically someone said the answer, well, now I can compute the sign, because that's my assumption. So now I compute the sign of the sum of this new Boolean function, g prime. Now if it turns out me I'm positive, what do I know? I know where this sum is relative to k. What's the next step? Binary search on k. I do it again. Now I ask, where is it relative to k over 2, right? And so on. That's the proof. Doesn't work for a 0, 1 function. Why not? That's sort of an obvious question, but why not? Yeah, it's always positive, or really it's that, yes, things can only add. So this whole thing doesn't work. Okay? Great. Yeah. Good. Yes, you can do essentially the same thing. Yes. Which is why I hesitate to say that it's definitely interference. Right. Good. Binary search on k and repeat. Okay, now here's where I'm going to sort of wave my hands rapidly because this becomes a little bit more difficult, but it turns out a really similar sort of binary search and padding argument suffices to show that it's sharp p hard to estimate the sum squared. That's a little bit non-trivial because this proof technique seems like it used the sign. And as I always say, even I can compute the sign of sum x g of x squared. Right? The answer is always positive. Right? Certainly never going to be negative if you're squaring it. But it turns out that's the fact that we use the sign here is sort of a red herring. That's not really the key point. In fact, you can run a very similar binary search and padding argument to show that computing the absolute value of sum x g of x is still hard. Okay, essentially the same thing. You can work it out in your free time, but then this really is just as hard as computing the square. Okay? All right, cool. So what do I want you to get out of this? If you followed the proof, great. If you didn't, the point is simply this. All I did is I had two problems, and they were approximate sum problems. One was a 0, 1 valued, one was plus minus 1 valued. Okay, they were exactly the same, they're essentially the same difficulty when I was exactly computing the sum over all inputs x of g of x or f of x. But when it comes to giving multiplicative estimates, one is much easier than the other. That's it. Okay. Cool. All right. Let me say this: the consequence. So there's remember there's a consequence of the fact that for the classical sum, approximating it is easier. This is the consequence for the fact that approximating the quantum sum is just as difficult. It's that estimating the output probabilities of a quantum circuit is sharp p hard. Okay. So why is that? It's actually really simple. It follows from the following claim: if I give you a quantum circuit C, estimating the output probability of that circuit is as hard as the squared quantum approximate sum problem. Does anyone see why? Can anyone just guess why that is? It's not super hard. Yes, the amplitude, and what is the amplitude squared? That's exactly why you're getting a square, absolutely, yes. But how are you getting the sum of x, g of x? In the amplitude? Through interference, yes. But what is the circuit? There's like a specific circuit I'm thinking about. Sorry?
There's like the intermediate sum over the y's.
Yeah. That's right. Okay, hold on. By what I call quantum Fourier sampling. It's essentially the basis of Shor's algorithm of almost every sort of quantum algorithm. Uses something similar to this. Here's the idea. Suppose I give you a function g. We're going to consider the quantum circuit that does the following. It's just really, really simple. It takes Hadamard's on n qubits. It's then going to apply the g in superposition, right? And it just takes another Hadamard, row of Hadamard's. It just measures all n qubits. What do we know about the probability that we see all zeros at the end of the day? Well, it's just the sum or x of g of x squared, but over something exponentially small, 2 to the 2n. Yeah? That's just a consequence of the fact that if I look at the Hadamard transform as a matrix, the first row, and for that matter, the first column, are all positives, positive one, right? So 1 over 2 to the n, whatever your normalization is, right? Yeah? That's all I'm using here. Now, but hold on. And this is probably the biggest mistake that you see in the media about quantum advantage. This doesn't give you anything by itself, right? And I want to be really clear about that. It's true that this is a hard quantity to estimate. But it's not the quantity that we care about. It's actually the quantity we care about is this sum. That's your quantum squared sum, right? Over 2 to the n, or in fact, 2 to the 2n. That means that the way we're going to argue about hardness of sampling from this distribution is not to sit there and repeat sampling. You're never going to see the all zeros outcome. It's true that if you could somehow compute the all zeros outcome, the probability of the all zeros outcome, you would get something really hard. You'd be able to, like, solve sharply hard problems and therefore break people's bank accounts and so on. But that's not what we do. We would be sitting there all day because it's exponentially small. Okay? Nonetheless, the fact that this hard quantity appears in the output probability is enough to argue that you can't sample from the same distribution. And that's the key point. It's the key point of all of the analysis of every quantum advantage experiment that we've seen so far. Okay, and I'm going to tell you how. Okay? Okay, so now we're going to put together these two consequences that I said, right? The first consequence, remember, was that the classical approximate sum problem was easier to estimate than it was to compute. The second consequence was that the, estimating an output probability, like all zeros of a quantum circuit, is as hard as the quantum approximate sum. Right? That's what we did with Fourier sampling. Okay, we're going to put these things together. That's it. That's going to give us our proof. Okay, it's a proof by contradiction. Let's assume, for contradiction, that there does exist an efficient classical sampler algorithm. That's exactly what we've been trying to show doesn't exist, so it's a contradiction. This means, okay, just by definition, this is what it means, right? For all outcomes y, the probability over the choice of random coin flips that the sampler equal y is equal to py of c. Yeah? That's what the quantum algorithm would do, but S is a classical algorithm. Okay, now, consequence 1. We know that estimating the probability that S outputs all zeros is strictly easier than sharp p unless pH collapses. That's consequence number 1, right? That's because it's a classical sum. Estimating a classical sum is strictly easier than computing a classical sum. That was consequence number 1. Okay, but we also know that multiplicatively estimating the output probability of a quantum circuit is sharp p hard because of quantum Fourier sampling. That was consequence 2. This is a contradiction. How can it be that giving a multiplicative estimate is both sharp p hard and also strictly easier than sharp p? That makes no sense. That's a contradiction. That says that there cannot be sampler algorithm. All right, I'm going to stop for questions. That's sort of the first part of what I wanted to talk about. That is the analysis of every quantum advantage experiment. Yeah.
The ones that were screwing up were like the ones that had cancellation.
Yes.
It reminds me a lot of like the Deutsch short cell. Is there a reduction?
No, there's not a reduction. In particular, these other questions that we had asked before in like the early 90s, they tend to be very similar, but strictly speaking, they're decision problems, right? So we were obsessing there in general with sort of putting a lot of weight on like a single outcome. A lot of probability mass on a single outcome, so we'd observe that with high probability. That was like, before quantum advantage, that's what we were thinking of. The realization here is that we actually don't need to do that, right? That sampling from a distribution in which a single exponentially unlikely probability happens to encode something hard is actually itself a hard problem. That's actually sort of profound. Yeah?
What if I ask like a what if?
Of course, yes.
So going back to how we define the g of x, are we able to redefine it? So this idea came because I didn't fully understand
fine.
the sum function.
Fine.
So the g of x minus k is inside of the sum, and we were able to separate the sums, and then the g of x takes the form of the f of x. So
no, it's not, I wouldn't say it's the, do you mean in the reduction it's an, I would say like when I was arguing about the hardness of approximating the g of x, it was, the g was always, g prime, all of the times I padded, it always remained plus minus 1 valued, right?
Right.
Yeah, okay.
Now, if we try to redefine that to, first of all, I guess, are we able to do that? Trying to redefine that g of x function so that it scales towards the f of x function?
No, right? We're never trying to do that, to be clear. Yeah. Right. Yeah.
So you didn't talk about anything about like this random SU force. Are you going to talk about it?
Right, that's coming next. So far, to be clear, this says nothing about random circuits. The circuit was not random, the circuit is fixed. In fact, I drew the circuit for you, right? Not a random circuit. Random SU4s are coming, yes. Yes, of course. There it is.
So G, I suppose we can, if we want to implement it, it can be a bunch of like multiple control Z.
Yeah, that's right, or they're like Toffolies or whatever you want, right? They're just classic, this is a classical function. Yeah, we're not going to implement that though, to be clear. That's not what the experiment is doing. This would be a much harder experiment than they actually end up doing. Yeah. This will come up in the analysis, but it's not. At the end of the day, what the experiment is a random circuit. But the reason it's hard is nonetheless going to have something to do with this circuit being there. We'll talk about, I'm purposely being vague because we'll talk about it. Yeah. Yeah.
I have like a weird question. I'm not fully convinced that these things are sorry.
Yeah. No, it's okay.
Like for because you said for like the quantum sum and the classical sum, there's a relabeling. So like a one-to-one.
That's right.
It's a one-to-one map from
That's right.
So like how can I not say that for like each one of the quantum sums that I want to solve? I'll just solve a classical sum.
Yes.
Like minus like
absolutely. Absolutely.
Yeah, so
okay, hold on. Let me first say it's a fantastic question. Such a fantastic question. It's on that very question is on the discussion problems that I'm going to give you. That strategy does not work. It fails. But it fails for a reason that you're going to find out. Okay? It's a great question, though. Others, yeah.
So second line of your contradiction proof right there.
Let me go there.
The first result, and had unless pH collapses. I might have missed it, but just so I know that like the proof is airtight. Can you explain like the unless pH collapses part?
Yes, I can. Let me explain it more sociologically than mathematically. Complexity theorists cannot actually prove anything unconditionally. Okay? So when we tell you that like something is harder than something else, like in this case, what we're really using is the first consequence. Remember, I was telling you that like right. When I was telling you that if you look at the classical sum, the exact classical sum we believe to be strictly harder than the approximate classical sum. That was consequence 1. That's actually a conditional statement on a complexity consequence called the pH not collapsing. That means we don't strictly know how to prove it without that consequence, but if this was not true, so if the pH did collapse, if that assumption was false, I always tell people like we'd have much bigger things to worry about than quantum advantage not being true. Okay. By the way, why do we believe this? You'll see this a lot in complexity talks. Essentially for the same reason we believe P is not equal to NP. Okay. So somehow, we believe this with like 95% certainty, whatever that means, but we can't prove it outright. But it's not a coincidence. We actually can never really prove these sorts of hardness results without some assumption, unless we like settle the biggest open problem in like complexity theory in the last 50 years. Yep. Okay, that's a good question though. Anything else? Okay, good. How is my timing, by the way? And what do I have?
So, up till 4:30.
Okay, cool. So we're okay. Should we be taking a break soon?
Whenever you want.
This would be a good time to take a break. So why don't we take a break? Come back and like. Okay, cool. Okay, so we just showed that you can't expect a classical algorithm to sort of take a quantum circuit and sample exactly from the output distribution of that circuit. Okay, that was the highlight. This is not what we do experimentally, though. The circuit that I just showed, the sort of Fourier sampling circuit. In fact, that circuit is like, there wouldn't be a huge advantage to using that circuit and this analysis over like Shor's algorithm, which is also fundamentally a Fourier sampling algorithm. So that's not actually what we do. And mathematically, though, there's also reasons that we wouldn't want to implement this, besides the fact that it's too hard experimentally and it's like Shor's algorithm and so on. It's sort of not robust. And what do I mean by that? Well, I sort of mean two things. The first is that it had this exactness assumption, which is really stringent. It's that it requires that the classical sampling algorithm, that S that I was talking about, right, samples exactly from the output distribution of every quantum circuit. How can I see that? Why is that? It's exact. That doesn't work if the distribution that the circuit samples from is like close to the output distribution of the circuit. It really need to be essentially the same distribution. Why? Sorry? Yeah, the exponent downstairs was what? It was exponentially small. So you could imagine like perturbing that distribution a little bit, right? So that like it's very, very close in what we call total variation distance, like L1 distance for distributions, but had no hardness whatsoever because we would just like wipe out that single like exponentially tiny probability. That's not something that's even close to implementable with near-term devices. They're like incredibly noisy. Okay. All right. And then the second thing is what I call the worst case assumption, which is that it requires that classical algorithm worked for all quantum circuits, right? As opposed to, say, most random quantum circuits or, single quantum. Where did I make that assumption?
You didn't specify the circuit.
Well, I did specify the circuit, right? It was that Hadamard, and then. But you're close. You shouldn't give up that easily. Like it's close. What I didn't specify was the G in that circuit, right? So in other words, maybe it's basically what you're saying. I think. Like I just giving you a hard time. So it's like that the circuit was all specified, but the G itself was not. And to be able to solve this problem, like to be able to invoke the hardness consequences of solving one of these, approximate sum problems or whatever, you'd have to do this for every G. That's a worst case result. And so when it comes down to implementing that circuit, you'd actually have to implement that circuit for every G, right? That's not very very appealing. So what we call a worst case result, okay? Which is, by the way, generally how we talk about complexity. But because we're implementing these things, we're going to be more demanding. Okay, so this is the major goal in the theory of quantum advantage, probably the most important unresolved question. It's to prove the impossibility of a much weaker algorithm. Okay, it's much weaker in two senses. It's approximate and it's average case. So what do I mean by approximate average case sampler? Well, exactly that. I mean, we're going to take an efficient classical algorithm, S. It looks the same as it did before. It takes a circuit C and a random string R, random coin flips, that samples from any distribution, I'll call it X, that's close, and let's say total variation distance, just like L1 distribution, distance for distributions, close, and let's say epsilon is sufficiently small, with high probability over this circuit. Right? So let's be really clear what this weaker algorithm does. I think about it as like, there's like a good day and a bad day, right? A good day with probability 2/3 over the choice of circuit, that sampler, S, outputs a sample from a distribution X that's close to the output distribution of that quantum circuit, which I'm calling DC. Okay? On a bad day, that's a good day. That's probability 2/3. On a bad day with probability 1/3 over the choice of circuit, it outputs a sample from a distribution X that's maybe not even correlated with D sub C. Okay? We want to say the goal, and the main goal of quantum advantage now for like almost 10 years, has been to prove that such an algorithm doesn't exist. Okay? So notice that we're now also talking about random quantum circuits, right? As the guarantee here is that this algorithm works with probability 2/3 over the choice of circuit C. What do we mean by that? Well, we could really mean almost anything, but in terms of the distribution, we're really talking about the distribution I showed earlier, when I said, what is Google doing? Where we're sort of looking at these 2-qubit Haar random gates, right? That's the distribution I have in mind. Okay? Oh, yeah.
Do you really care about the specifics?
No, no.
You actually use the whole Haar random family.
Very interesting question. I don't care that it's Haar random necessarily. I do need a continuous degree of freedom. Like I do need a continuous distribution. Strictly speaking, I don't know how to make the arguments I'm about to show work when we consider like, discrete distributions. Like, with probability 1/3, you implement this gate. Probability 1/3, implement this other gate, and so on. You need some continuous degree of freedom.
But the ones that they have discrete? Or?
They are discrete. That's a little gap. Believe me, though, it's not even close to the biggest gap between the theory and experiment. It's not what I'm worried about.
So they have the continuous single.
Yeah, that's right. They do have some continuous degrees of freedom, and we'll give them the benefit of the doubt that they could probably do something like this. Like the 2-qubit gates being Haar random is not actually necessary for my arguments. I just need some of the gates to be continuous. This is, again, yes, I think there is a little gap here between theory and practice, but it's not even close to the biggest one. Yeah. Any other questions? So it's kind of clear what I mean by approximate average case sampler? This is a weaker notion than before. Yeah.
Is it clear that total variation distance is somehow like the right?
No, it's not. It's not clear. What is true is that this particular argument is not super sensitive to the thing. You can imagine like other metrics, maybe not any metric, of course, but it's not sensitive. But in fact, in fact, there's this question. I think I was going to say this next, actually, which is, it's one of my biggest pet peeves in this area. Many times people just take for granted that the main reason we're thinking about approximation in terms of total variation distance is to model noise. I think intuitively that's sort of correct, but in actuality, it's an excessively poor model of noise, right? We're only modeling noise by bounded total variation distance. So here's what I say. I'll explain this in a moment, but I'd like you to think about that. So I don't think this is the real reason that we're thinking about total variation distance like this is to model physical noise, but rather something I'll call classical imprecision. Let's forget what that is for a moment. But any ideas why it's sort of a bad model of physical noise? Yeah, noise is depolarized, but I mean, you can always say, okay, so you fix your favorite noise model. Maybe it's depolarizing noise. I don't know, whatever it is. Well, there's always going to be some total variation distance, right, between whatever the noisy distribution is and the ideal distribution, right? You can always say, like, you can always take the total variation distance, and it's something, but that's not really what we're saying here. And yes.
Like if you have like constant rate, maybe
yes.
Like just swarm the result.
Yes. Precisely. The problem is what we mean when we say less than or equal to epsilon. What we really mean here is that there's like a fixed constant, like say like 1/3 or something like that. It doesn't really matter. 1 over 100. And we're always talking about asymptotics as complexity theorists, right? So what does that really mean? That means it's exactly what I was talking about earlier, in fact, right? That means you're taking the system size to infinity, yeah? You're not changing the error. That's a crazy thing for near-term quantum experiment, as providing that your gate error rate stays the same. So I don't actually think that's the reason we do this. I think the reason we do this that's much more compelling is to think about what I call classical imprecision, which is the idea that, at the end of the day, we're trying to understand why are random circuits hard at all? Not at all obvious, right? And if you think about them from a classical perspective, the hardness of classically simulating them, it makes a lot of sense that a classical algorithm, like say a tensor network algorithm or whatever your favorite classical simulation algorithm is, that if it sort of runs for a longer amount of time, it would be able to simulate that circuit more accurately, right? Total variation distance is actually a reasonable model of what I call classical imprecision. That's the error that's made by a classical algorithm simulating a quantum circuit. It's not such a great model of physical noise, okay? We think a lot about how to make these results robust to physical noise. I don't know if I'll get time to go over that, but that's I think it's a totally different ballpark, okay? It's still very important to consider this total variation distance because it models classical imprecision. Any questions before I go on?
Small note. Can you just say because it doesn't model physical noise in a good way because like in a physical setting, we want to like measure the distance between two different quantum states. We're like only the distance between
good.
the instruments. So.
Yes, I don't actually buy that. It's a good. I understand what you're saying, but here's the problem. So so people, in fact, physicists come to me all the time. They say, hey, look, we care about fidelity, which is actually what you're saying. I think some notion of overlap between two quantum states, right? Why don't you just forget about total variation distance and use fidelity, and then we'll all be happy? Like that's what the physicists actually try to measure. They measure fidelity. They don't measure total variation distance, not directly at least. The problem is that there's no classical equivalent to fidelity, right? Fidelity is a quantum property. It's a quantum measure. So the problem is here, we're talking about how do we model a classical algorithm that's supposed to be sampling from some distribution that's close to the classical distribution that the quantum circuit is sampling from, in some sense, right? So fidelity is actually meaningless here. I don't know what it means, And as soon as you make it try to make sense, ends up being essentially total variation distance. Yeah. What else? That's a really good question, though, and I get that all the time. Yeah. Okay, let me keep going. Cool. So how are we going to prove this new result? Well, again, we actually can't prove it. It's been open for a long time, but we've gotten better and better results, closer and closer to what we want. So it turns out the central problem of study here is what's called the delta random circuit estimation problem. Delta is a parameter. And here's what it is. It's rather than sampling, it's sort of a computing problem, okay? But it turns out that this is related to sampling. And it's the following. So we're given as input a random circuit C, okay? And then our goal is to output an estimate Q to the output probability of C. So the output probability, I'm just by convention, it's just the probability you see all zeros. It could be any outcome, it doesn't matter. With an imprecision delta with probability 2/3 over C. So again, there's this problem. You think about a good day and a bad day. Good day, you have 2/3 of the probability over C. You output a delta estimate to the output probability. Bad day, 1/3 probability over C. You output nonsense. Doesn't have to be correlated with the output probability. And the question is, how hard is that problem? Okay. Oops. Okay, so it turns out, I'm not going to get into this, but this is essentially proven using the Stockmaier theorem that I gave before. But we'll just sort of gloss over it. So to prove this hardness of this approximate sampling, which is, again, sort of the major goal of the theory of quantum advantage, it suffices to prove that the delta equal 2 to the minus n random circuit estimation problem is sharp p-hard. Okay, that's the goal. Why 2 to the minus n? Why is that our precision? It's essentially 1 over the Hilbert space dimension. So you have an n-qubit system, you have a 2 to the n dimensional Hilbert space. That's the goal. Now, we've been trying to prove this theorem that this problem is hard for, oh man, I don't know, since 2010, something like this. We still can't get it. We've gotten a lot better, though. So let me give you sort of a timeline of our results. The timeline is going to be in terms of the precision, and we'll see that the precision is growing because larger precision hardness result is stronger result, right? So with respect to a random circuit C that acts on n qubits, and we're always going to think of the size as m, okay, like Mary, which is n times d. So we're always going to take the size of the circuit, the number of gates, right, to be n times the circuit depth. That's what I'll call m, okay? So here's what we can show. In our first paper on this, we didn't even bother to quantify the full precision. We just said, okay, the imprecision is some 2 to the minus some polynomial in m. Okay. There was a follow-up work by Ramis Movasag who showed that, in fact, he sort of quantified that precision. He showed that we could show that the delta, or he could show that the delta equal 2 to the minus O of m cubed problem is hard. Okay. We worked really hard for 2 years and had almost no progress. And then relatively recently, 2021, we've been able to extend this to 2 to the minus O of m log m. Okay? And in 2022, there was at least a claim that we haven't really been able to follow fully, but a claim that the 2 to the minus m problem is hard. We're still off by our goal. Now, it turns out we can always think about the depth, and this is sort of non-trivial. We can think about the depth as constant. Sufficiently large constant, which means that m is a constant times n, okay? That means that we're off by, if you believe this result, you're sort of off by a constant in the exponent of what you want, okay? But strictly speaking, we don't have what we need to go from the hardness of computing, right, to the hardness of sampling. That's why we want this 2 to the minus n. Okay. Okay. Now, in boson sampling, boson sampling is this linear optical experiment that's now been implemented by USTC and Xanadu. The situation is sort of similar. The goal changes just because the Hilbert space dimension in these optical experiments is different. It's more like 1 over e to the n log n, whereas it turns out we have hardness in our 2021 result at 1 over e to the 6n log n. We're off by a factor of 6 in the exponent. If you've been like me and you've been working on this problem for like 10 years, seems very close, but we actually think we also know reasons why getting rid of this 6 might be hard. Okay? This is a big open question. Okay, cool. So how do these results work? It turns out they work by adapting really, really nice proof, a very simple proof due to Dick Lipton in the classical complexity world that shows the average case hardness of computing the permanent of a matrix. So bear with me, let me show this proof because it's one of my favorite proofs. I think it's something that everyone should know. It's just very simple, but I think very beautiful. And let me remind you, so what is the permanent? Well, the permanent of the permanent of an n by n matrix is sharp p hard in the worst case. It's a really famous result in complexity due to Les Valiant in the 70s. The permanent looks a lot like the determinant, right? It's the same, in fact, as the determinant, except it doesn't have this weird sign of the permutation, right? Outside the product. And one of the big mysteries of complexity theory, which is unresolved, is why somehow taking away that sign makes us go from the determinant, right, which is easy, you can solve it in polynomial time, to the permanent, which is not only NP hard, but sharp P hard. It's even harder than NP hard. So somehow it makes it, there's a huge gap in difficulty. We don't really understand why that's happening. Okay? You can say, well, okay, the algorithm doesn't work, Gaussian elimination doesn't work here, but we want more than that. We want to say, why exactly is the permanent so much harder? We don't really understand that. It's one of the biggest open questions in complexity theory. Okay, but anyway, nonetheless, Valiant's result is worst case hardness. And as I sort of alluded to before, worst case hardness means that what Valiant really showed is that you can't expect a classical, or for that matter, a quantum efficient algorithm to compute the permanent on every matrix, right? Whereas what we're going to do, what Lipton does, is he boosts this hardness from worst case hardness to what we call average case hardness. Average case hardness is the hardness of a random matrix, computing a random matrix with sufficiently high probability. Okay? There are very, very few problems that have explicit worst to average case reductions, or in other words, for which we understand in complexity how hard the average case of the problem is. This is one example. This is why I like it so much. Okay? Sort of a gold standard of hardness. We want average case hardness. Don't know it that often. Okay, so anyway, what does Lipton do? He uses this algebraic property to boost the hardness of the permanent from the worst case to the average case, which is a much stronger notion. And it's very simple. It's that the permanent is a degree n polynomial in n squared variables. The n squared variables are just the n by n matrix entries. Right? And then it's not hard to see, if you look at the expression, that this is a degree n polynomial in the n squared variables. Okay? All right, cool. So now what's the setting of average case hardness? Let's just be formal. I think I've said this informally, but this is what we're trying to do. Our goal is to compute the permanent of a worst case matrix X. It's just a complexity theorist way of saying an arbitrary matrix. You give me a matrix. I'm going to think about this as a matrix with elements in a sufficiently large finite field. Okay? But you give me that matrix, over FQ or whatever. Okay, but I don't know how to compute that. I really want to compute the permanent of that matrix because we know by Valiant's theorem that's hard. I don't have that ability though. The only thing I have in my hand by assumption is this sort of faulty or average case algorithm O that correctly computes most of my permanents on average. Okay? In other words, this is what O does. It's given as input a random matrix Y, and it spits out the permanent of that matrix correctly with high probability over Y. Okay? And the goal is, but we don't know when it works and when it doesn't. We just know that most of the time it works. Yeah? And so the goal is to use this faulty or average case algorithm O to correctly compute the permanent of my favorite matrix, X. That's the goal. Because that would show that the average, on average, the permanent is as hard as it is in the worst case. We know it's hard in the worst case. Okay? So how do we do this? It's a very slick argument. It's just a polynomial extrapolation argument. So here's the idea. Let's choose n plus 1 fixed non-zero points in our field. I'll call them t1, t2 through tn plus 1. And then a uniformly chosen and fixed matrix R, okay, in my finite field, okay? All right, now we're going to consider a line, which I'm going to call A of t. It's x, that's the worst case matrix, the matrix I want to take the permanent of, plus t times R, right, just shifting it. 2 observations about this line, and once we have those observations, the proof is essentially done, okay? First, I call it a scrambling property, which is that for each I individually, A of t sub I is a uniformly random matrix over our field. Well, why is this? Well, it's not so hard to see. What did we do? We took x, that's our worst case matrix, and we shifted it by t times R, by some random thing, right? And all we're saying is that, if we just look at this individually, this is now, A of t sub I is a uniformly random matrix over our field, right? Because we took a fixed matrix, we shifted it by something random. Doesn't matter that we have a shift. It's random, okay? Cool. Second observation, we call it the univariate polynomial property. It's very simple. It's that the permanent of A of t is a degree n polynomial in the single variable t. Okay, that's not hard to see either. That's inherited from the algebraic property of the permanent, which is that the permanent itself is a degree n polynomial in n squared variables. So not at all hard to see just by looking at this expression for permanent, that permanent of A of t is a degree n polynomial in single variable t. Okay. What do I do? Any ideas? So I have these, okay, so hold on. I have n plus 1 points, my finite field, right? It's a degree n polynomial. Any ideas what I would do? Yeah, that's right. So what I'm going to do is I'm going to use this faulty box that works, to compute most random matrices, the permanent of most random matrices, to evaluate the points, permanent of A of t1, permanent of A of t2, and so on, n plus 1 times. Okay. Now, right, these n plus 1 points that I get from my faulty box, from O, uniquely define the polynomial, because it's a degree n single variable polynomial specified at n plus 1 points, right? So now I use polynomial extrapolation. I'll call this Lagrange extrapolation, just whatever you learned in like middle school or whatever, right? It's sort of the naive way that you would extrapolate polynomials to reconstruct the coefficients of this single variate polynomial permanent of A of t. Once I have that in my hand, I simply evaluate that at 0. And that gives me back the permanent of my worst case point, right? Because when t is 0, A of 0 is x. Okay, but why does this work? It's not totally clear because the box is faulty. It makes errors. But the reason it works is because I was sort of a little bit slick here, and I made this algorithm, this faulty algorithm, work with very high probability, like 1 minus some polynomial. And the point is, if that polynomial is sufficiently small, like 1 over 100 times n or whatever, by a union bound, right, with probability, it's a bounded probability, say 2/3 or whatever, it's actually, that box is actually going to be right on all of my n plus 1 points. When it's right on all of my n plus 1 points, the game is over, right? Because I use this argument. But I want to be really clear, this argument it's very important that we have sufficiently high probability here, okay? Now, it turns out that, I have to say this, not super relevant to what I'm going to say, but because I sort of love complexity theory, it turns out that by using much more sophisticated techniques from classical error correction, you can actually make this very similar result work, even when instead of 1 minus 1 over poly, this is 1 over poly, which is actually quite amazing. It's sort of saying, even if this faulty box is so faulty, it's essentially never right, right? You can still like extract the permanent of our worst case matrix. That's quite amazing, but it's very deep. That's not something that I can say in this slide, okay? Uses something called list decoding, if you know what that is. Great. So what are we going to do? Well, we're going to take this result of Lipton, which applies to the permanent of a random matrix, and we're going to apply it to random quantum circuits. So rather than thinking about the permanent of a random matrix, we're going to try to use it to show the hardness of computing the output probability of a random quantum circuit, like the ones that Google is talking about. Yeah?
So in the last part, you said if it's too faulty, then also we can extract. And I'm thinking like, what is the reason behind that?
Oh wait, say it one more time. I didn't quite hear.
If it is like 1 by poly n, which is like very faulty, then also we can extract the permanent easily, right?
Yes, that's what I was saying.
So what is the reasoning behind that?
No, yeah, I didn't really tell you, right? I said, okay, it uses some very sophisticated error-correcting results, something called list decoding. I didn't get into that. That's really cool. You should read about it. It's not. It's gonna, that would take like another 2-hour lecture to understand that. Yeah. Cool. We're going to use the much more the much simpler version. Okay.
I had a question about the. What is the best algorithm that we have to do that?
To compute the permanent. Yeah. So you can compute the permanent in essentially 2 to the n time, which is better than the naive like n factorial time.
Yeah, I see.
Yeah. But it depends a little bit what you mean. So if the permanent, for example, has like if the matrix has all positive entries, and you're talking about real numbers that are positive, then there's actually good efficient approximation algorithms for the permanent. So it depends a little bit what you mean. Mm-hmm. Cool. Okay. So what are we going to try to do? Well, the thing is, we don't actually know that many results like Lipton's result, which is arguing natively about the hardness of computing the permanent of a random matrix. That's super strong. That's like a gold standard in complexity. And so that's our starting point. We want to adapt this from the permanent of a random matrix to the output probability of a random quantum circuit. It's the only thing we know is Lipton's argument. But one thing we started realizing when we looked into this is that actually the permanent is not so different mathematically from the output probability of a random quantum circuit. In what sense? Well, it turns out the output probability of a random quantum circuit, much like the permanent matrix, has polynomial structure. And to see that, we're going to break apart the circuit C into its 2-qubit gates. So it's like Cm times Cm minus 1 and so on. These are 2-qubit gates. And the polynomial structure comes from the path integral, right? Which says that we can write the output probability, or let's say the output amplitude, right, of a circuit as this ginormous sum, right? It's a sum over an exponential number of paths. In other words, this term has, the number of terms is exponential. But the key point is the value of each of the paths is actually, it's manageable. It's the product of m gate entries. Okay, that's not hard to compute if you have in your hand the circuit. And so it's a polynomial of degree m. M is the size of the circuit, the number of gates, in the gate entries of the circuit. Okay? And so, what we really care about, of course, directly is the probability, not the amplitude. So by the Born rule, we can square it. Let's just assume things are real. You don't need to make that assumption. But it's a polynomial of degree 2m, just increased by a factor of 2. Okay? All right. So we have, just like Lipton, we have a similar sort of polynomial structure. Now, how do we use this structure to adapt Lipton's proof? Okay. Well, what's the idea? What made Lipton's proof sort of work? Well, what he did is he wanted to take a random, he wanted to understand the permanent of a fixed matrix over his finite field. But by assumption, he has the ability to compute the permanent of a random matrix, right? So the whole point is we want to sort of take that fixed matrix and scramble it to make it look more random so that we can use our box that works with high probability, right, to compute the fixed matrix. We want to do something very similar to that, right? We want to take our, you give me your favorite worst case circuit. You say, compute the output probability of that. But I only have the ability to compute an average case or random quantum circuit with high probability. So what do I want to do? Well, clearly I want to scramble that circuit. I want to make it look more random to somehow use the ability to compute random circuits to then compute the worst case circuit, like Lipton does. Okay? How are you going to do that? Well, here's an idea. It's not quite going to work, but it's very close. Let's say we have an m. Our worst case circuit has m gates. Okay, C1, C2, and so on through Cm. We're going to fix m Har-random 2-qubit gates. So we'll call that H1, H2 through Hm. So one Har-random 2-qubit gate per 2-qubit gate in our worst case circuit. Okay, we're going to fix it. All right, now the main idea here is to scramble C by implementing a tiny fraction of the inverse of each of these Har-random gates. Okay? What do I mean by that? Here's what I mean. Well, for each I, in the ith gate in our worst case circuit, we're going to consider what I call Ci prime. It's a scrambled circuit. And Ci prime by definition is going to be Ci times Hi. That's the worst case ith gate, right, times the Haar random gate. Well, if you know anything about the Haar measure, right, if you ignore what comes next, which we'll get to in a moment, this scrambles completely. If you multiply a fixed gate by a Haar random gate, by the definition of the Haar measure, in fact, you get something Haar random, right? So at this point, we've scrambled completely. But we want to do a little bit more for reasons that will come next. We're going to multiply by e to the minus I little hi, which is, by definition, it's going to be the log of hi, times theta, which is some real parameter. Okay? So this is how we're going to scramble. Why does this work? Well, it doesn't quite, but it's very close. Well, it has a very Lipton-like structure to it. Why is that? Well, notice if theta is really tiny, if it's very close to 0, right? Well, then what have we done? Well, if theta is super tiny, right, well, we've done essentially nothing, right? And because we've done essentially nothing, right, well, we're very close to Ci times Hi, which is completely scrambled by the invariance property of the Haar measure, okay? But if theta is not tiny, if it's 1, then what have we done? If theta is not tiny, if it's 1, then we've taken Ci times Hi times e to the minus I little hi. That's also known as Hi inverse, right? And that cancels Hi, and it gives us back the ith gate. So it gives us back our worst case circuit. So this is very, very similar to Lipton. And it's not by coincidence. This is inspired by Lipton's proof. The point is that we have this single parameter theta, and sort of extrapolating from totally random circuit on the one hand, when theta is tiny, to a fixed worst case circuit when theta is 1. Okay? So what comes next? And I'm purposely vague here because this step doesn't quite work, but it will work in a moment. Well, you can imagine then doing very similar to what Lipton did with this structure, right? You can imagine taking, you remember this is a degree 2m polynomial, right? Because that's using the path integral. So you can imagine taking like 2m, several non-zero but small thetas, like theta 1, theta 2, and so on. For each one of those thetas, you get a new sort of random but correlated circuit, which I'll call C prime theta 1, C prime theta 2, and so on, right? You then use the ability, right, the assumed ability to compute the output probabilities of a random quantum circuit, high probability, to compute the probabilities of all of these circuits, each one of them, right? Then you use some polynomial extrapolation, just like Lipton did, to reconstruct a polynomial in the single variable theta. When you do that, you evaluated it at theta equal 1. Theta equal 1, by definition, gives you back your worst case circuit probability. Okay? This almost works. So, by the way, if you don't follow, I'm just doing exactly the same thing as Lipton did, but with a slightly different way of going from the worst case circuit to the random circuit. Okay? Cool. It doesn't quite work just for a really simple reason, which is that e to the minus I little hi theta is not a fixed degree polynomial in theta. It's just not. So what would a physicist do to solve this problem? I think you heard a lot about this earlier. Absolutely, right? It's exactly what we're going to do. It fits well with the theme of today. So we take a fixed truncation of the Taylor series for e to the minus I little hi theta. In other words, here's the final way we want to scramble the circuit. We take the ith gate of the worst case circuit, Ci, we multiply by hi, and then instead of multiplying by exactly e to the minus I hi theta, we multiply by the kth order Taylor series truncation for this unitary, e to the minus I little hi theta. Okay, now we actually are finished. Why is that? Well, almost. We're almost finished. Why? Because each gate entry now is a polynomial in theta. Why is that? Well, because the Taylor series is a fixed degree polynomial in theta, right? And then by the path integral, right, the Feynman path integral allows us to write the output probability, nothing more than polynomial in the gate entries, which are now themselves polynomials in theta. So the output probability is polynomial in theta. Okay? This works. Now we can extrapolate. We reconstruct the polynomial in theta, and we evaluated at 1. We evaluated at 1 because that gives us back the output probability of our worst case circuit. Okay? Okay, but there's a big problem here, right? This is sort of very elegant, but we now have to pay for the fact that we truncated the Taylor series. What happens sort of mathematically when you do that? So we took a unitary gate, yeah, e to the minus I hi theta. We truncated its Taylor series. What happened to it? It's not unitary anymore. That's a bit problematic, right? So in fact, strictly speaking, what we showed here mathematically is that, outputting, we gave hardness evidence for simulating not a random unitary circuit, but a random slightly non-unitary circuit that's very close to the unitary circuit. Yeah?
Can you find the nearest unitary to the matrix that
it's okay, this is historical. Something like that has already been done, and I'll get there in a moment. Okay, but so we have this problem, right? Because a skeptic could say, well, you just showed some hardness result, but to show your hardness result, you actually made the unitary non-unitary. Couldn't the hardness all be involved in that non-unitarity? Because we know actually from experience that non-unitarities if your operators are non-unitary, you can actually get a lot of hardness from that. Okay. Well, it turns out the answer is no. What I just described was like the introduction of our paper, and the next 20 or 30 pages of the paper end up sort of arguing that that's not the case. So in fact, what we were able to prove is the following. So remember, what we cared about at the end of the day was not the hardness of exactly computing the output probability. Instead, we care about this estimation. Remember the delta I showed you in the timeline and so on? So the key point is what we were able to show is that since what we really care about is some additive estimate, delta, to the output probability, then in fact we can formally prove that with respect to that estimation problem, it actually doesn't matter in terms of hardness if we're talking about the output probability of the truncated circuit, C prime, or the nearest unitary circuit, C. It's in fact the same complexity. Intuitive, it's a very hard, very technical proof. Intuitively, it's super simple though. It's because the truncation error that we're incurring when we truncate the Taylor series, it's so much smaller than the size of the additive error where sort of conjecturing is hard, right? So here's sort of the way I think about it graphically. We're sort of arguing that computing the output probability of this truncated circuit, C prime, is sharp P hard. It's super, super close, like 2 to the minus n over some exponential close to the output probability of the unitary circuit, the closest unitary circuit. Hold on for a second. Okay? But then we're conjecturing, because we want to talk about the hardness of sampling, that outputting anything in this much wider window of width, like 2 to the minus n, is hard, right? And so what we can prove is, if that's really what we care about, the hardness of sampling, and so we care about the hardness of this level of estimation, it really doesn't matter if you talk about this circuit here, the truncated circuit, or this. And in fact, it's an if and only if. So it's really, we don't lose anything, it turns out, by talking about the hardness of this truncated circuit. But it's very non-trivial. One thing I'll say is it's very non-trivial. It takes us like 20 pages. Luckily, though, it's historical. Okay? So more recent, in follow-up work, Rami Smovasag had some very nice papers that showed a very similar argument. Still sort of uses this Lipton idea of sort of extrapolating, but the thing he changes is the path that, the way he's sort of the single parameter path that goes from the average case circuit, the random circuit, to the worst case circuit. He shows a different way to do it that he calls the Cayley path. I'm not going to get into the details, but the important thing about that is it stays unitary throughout the entire path. And so he doesn't have to worry about this. I want to be clear, he comes to the same conclusion that we do, but in like 5 pages instead of 30 pages. Okay, so the analysis is what's changing, and it's very nice that we can do that. Well, okay, is there a question? Yeah?
So when you're using the Taylor series, you're assuming theta is small.
Yes.
But when you're evaluating at theta equals 1.
Yes.
So 1 is not small, right?
1 is not small.
Yeah, so
right.
How can you justify that?
Good. We're going to do that. Okay, first of all, we're going to be punished for that. How are we going to be punished? That's exactly the difficulty to making these results robust to additive error. It turns out we're not punished at all if we're talking about exactly computing or very nearly computing each of these points. And that makes sense. If you're computing them to a huge degree of precision, shouldn't really matter how far your evaluation point is, because you're essentially getting the exact same polynomial. But the really interesting question that's in fact so interesting it's going to be the next topic of my next 5 slides is the robustness of this argument. And there we're going to be punished very dramatically for this problem. That essentially we're evaluating this polynomial in approximately at certain points, not exactly, and points that are very far from the extrapolation point. Right? We're evaluating very close to 0, and we want theta equal 1. And that's going to be precisely the issue with why these robust. It's so hard to prove that these results are robust to error. Yep. Anything else? Yes.
Relatedly.
Yeah.
Do these Cayley path arguments cost you more in robustness?
They did in the beginning, and then they've been sort of tweaked. So right now they don't.
Okay.
Right now they don't. But this took years and years of work. Yeah. Yeah. Anything else?
Yes.
Yeah.
Do we assume like M is party size of N?
Yes. Precisely. So M for us, because it's a poly-size circuit, so M is going to be a polynomial. In fact, it may even be a really small polynomial. Like I said, I'm thinking about M as like N times D, N times circuit depth.
Like when we consider the efficiency of classical algorithms, in poly-size is also poly-size.
Yes, everything is poly-size, exactly. So what I was saying is not only could it be an arbitrary polynomial, it could even be like a reasonably small polynomial, like maybe M is N times 5 or something like that. Yeah. Good? Cool. Okay. I don't have that much time, but I would like to at least, with the time that remains, I'd like to at least sort of bring you up to speed to some degree with the sort of more modern stuff. So this was like 2018 is where we stopped. And since then, we've been thinking a lot about how to make these results more robust to imprecision. It's exactly what we talked about before. The reason is because right now they're talking about the hardness of computing, but we really want to talk about the hardness of sampling, because that's what the experiment does. The Google experiment does not compute output probabilities, right? There happens to be the Stockmeyer reduction, which works when the precision is sufficiently large, when it's 2 to the minus n. But we're not there yet, like I said. That was the whole point of my timeline. OK, cool. So what's the issue? And I already sort of said this, but let's go through it a little bit more specifically. So far, we sort of assumed that we've had the ability to compute the output probabilities of each of these random circuits. So that's these like random but correlated circuits, C prime theta 1, C prime theta 2, and so on, exactly. OK? But that's not actually the setting we care about. The actual setting we care about, we're given these 2m evaluation points, which I'll call theta I, yi, and they're approximate. So we're given that for all I, right, the ith evaluation point is, delta approximates the output probability of the ith circuit. Okay, that's what we're given. We wanted to say, we want delta to be as large as possible. In particular, we want it to be 2 to the minus n, right? Because that's the 1 over the Hilbert size. 1 over the dimension of the Hilbert space. OK, so in actuality, the way we really should be thinking about this is we have 2 polynomials, not 1. We have the ideal polynomial, which we don't actually have direct access to, right? I'll call that P. So that P of theta I is equal to the output probability of the ith circuit. Okay? We'd love to get our hands on that polynomial, because then we would simply evaluate it at 1. And that would be, by construction, the output probability of our worst case circuit. But life is not that simple for us. Instead, we're given the extrapolated polynomial, which I'll call Q. And what we know about that is that comes from Lagrange extrapolation, right? What we know is that Q of theta I is equal to yi, these approximate points. Okay? So actually, this is a very nice mathematical framework, right? And it's something like this. The question is, well, we're given access to these red points, right? And what we know about these red points is that in a sufficiently small window of 0 through theta max, right, those red points well approximate, they delta approximate the polynomial, right? But we don't, and this is what was said earlier, it's why it's a perfect segue. We don't really care about that, though. We care about this way over at 1. And just was mentioned, right, we should be punished about that. That should not be something that comes easily for us, right? And so the mathematical question is, if you have 2 polynomials, one is P, that's the ideal polynomial that we care about. One is the extrapolated polynomial, that's the blue one that we have access to. If all we know is that we're close in some window, how close are we all the way at 1? Right? That's the question. Now, it turns out This is answered by something that's called the Paturi picture, due to this really fundamental result in a field called approximation theory, the early 90s by Paturi. It's just a mathematical result. It says the following. Suppose we have a degree d polynomial, I'll call it z, okay, in a single variable, which for convenience I'll call theta, okay? And it's bounded in an interval, 0 through theta max, by delta, okay, whatever it is. Then all the way at 1, z of 1 is less than or equal to delta times 2 to the degree of the polynomial times theta inverse of theta max inverse, okay? So why is this the right theorem for us? Well, maybe it's sort of clear. We're going to consider the degree 2m polynomial, which we'll also call z, right? Which is just the difference polynomial. It's the difference of the ideal polynomial, give me a second, and the extrapolated polynomial, q, okay? And then our picture looks something like this. We know, since we're now thinking about the difference, we know that in this tiny window, that polynomial is bounded. It's bounded by delta, okay? But we don't care about this tiny window. We care about it all the way out at theta equal 1. The question is, how large can that be? That's what Paturi is answering. Paturi is giving us an upper bound, saying that at 1, the difference between these polynomials, or if you will, the error that we're making on our worst case circuit, is bounded by delta, that's our imprecision, times 2 to the degree of the polynomial times delta max, theta max inverse, okay? So what Paturi is saying is that if our goal is to shrink the value of the polynomial at 1 to reduce the error that we make on our worst case, the output probability of our worst case circuit, we can do, if we want to reduce that, we really should focus on either reducing the degree of our polynomial or growing, making larger this window, theta max, because then theta max inverse is smaller. And that actually serves to reason, wouldn't you say? Like if you want to sort of minimize how small this is, well, you can make the degree smaller, fine, or you can try to make theta max much closer to 1. And that's what it's saying. Okay, let me take a question. Yeah?
I just want to sanity check this bound. Is the only reason that this is not a vacuous bound because we're in the interval 0, 1? Because polynomials can never blow up like exponentials.
Right, exactly, that is. So it's very important that we're scaling things correctly because, of course, over the long haul, we're polynomial, so we're not going to be bounded exponentially. Yeah. Right? Right, absolutely. Let me also say that in many cases, this is not a tight bound. In some cases, it is. Yeah. Because it's an upper bound, right? Yeah. Hey, yeah. It is. In fact, this similar problems come up either in learning theory or in error correction, right? You can also think about this as related to error correction because you sort of have these noisy points and then you sort of want to extrapolate the ideal point. So it's really common. It comes up all over the place. Other questions? These are good questions, though. Others? Yeah.
This is a little unrelated to this, but can you do a similar proof for exponential functions rather than just polynomials?
Good. That depends on a lot of different things. In particular, it turns out it depends on the size of some of the coefficients that you're talking about. Yeah. So no, I would say generally no, but there are some special cases. Yeah. Questions? Yeah.
How sensitive is it to the fact that like you somehow use like a polynomial, like a power series approximation to the exponential, like if you had Chebyshev?
That's what I'm saying. Yeah, it turns out not to be that sensitive because the errors we're going to be trying to tolerate are so much larger than the degree that we can approximate by the Taylor series. Yeah.
And also like, maybe this is true, but this H operator, we are assuming it's a sufficiently nice operators so that like it doesn't matter where we are evaluating it, right? Like there is no non-analyticity anywhere.
Yes. It turns out you have to prove that. And that requires some special properties of the polynomial we're considering. It's not true in general, but absolutely I'm shoving that under the rug. Yeah. Yeah, you have to be careful so that it's sort of sufficiently nice in this window. Right, exactly. Okay, cool. So, here's the way we think about this. You want to improve the robustness of this argument, you either can reduce the degree or you can make theta max larger. The degree is going to be really hard to improve because the degree comes from the polynomial, which comes from the path integral. We don't know of another polynomial, so it's really hard to reduce the degree. So the real question is, what's constraining theta max, right? Sorry? Actually, that's not the problem. You could imagine it, but no, it's not. What it turns out it's constraining theta max is the following. It's the fact that we were using Lagrange extrapolation. So Lagrange extrapolation was forcing us to get all of these points correct. Remember we were using the union bound and saying that like if the probability of the algorithm is sufficiently high, with probability 2/3 or whatever, all of the points are correct, okay? Well, what does that mean? That means that we really need the faulty algorithm that's computing these output probabilities to succeed with really high probability, like 1 minus 1 over m, okay? M is the degree. Maybe it's 2m, but it doesn't matter, okay? But we're going to be punished for that, though. Why is that? Well, because as theta gets larger, so as we take theta max in particular, that's the largest theta to be larger, well, if you remember how we scrambled the scrambled circuit gets less and less random. I mean, that's not hard to see, right? Because remember at theta equal 1, it's not random at all, right? So where is that coming into the picture? Well, that's coming into the picture in terms of how we can set theta max. How do I see that? Well, now here's some things you're just going to have to sort of buy. You can look at the proofs in the paper, but I think they're pretty believable. So it turns out you can ask, how is the circuit C theta prime distributed? Well, it turns out it's not Haar random. It turns out it's m times theta close in total variation distance from a truly Haar random circuit. Okay, that sort of makes sense because each gate individually is like theta close, and we have m gates, so that's why we're getting m times theta close. Okay, well, what that means is that the algorithm works a little less well on points that are closer to 1. That's what you'd expect, because the algorithm, by definition, works well on random circuits. It doesn't necessarily work on the worst case quantum circuit. So as you make theta max larger and larger, closer and closer to 1, it works less and less well. So turns out it works. You can just, this is actually a general fact, you can subtract the total variation distance. So it works with probability 1 minus m times theta on these points. Okay? So what does that mean? Well, let's just do algebra. If the algorithm works with probability 1 minus m times theta, and you want m times theta then to be 1 over m, what does it mean about theta? It means you want to take your largest theta to be less than 1 over m squared, so that m times theta is less than 1 over m. It's just algebra, right? Okay, so that's giving you your bound on theta max. Now we plug in Petury's bound, right? Well, Petury's bound says that z of 1 is less than or equal to delta, that's your imprecision, times 2 to the d, that's the degree of the polynomial, times theta max inverse, which in this case is d is like m, like 2m, whatever, right? Theta max inverse is m squared. Or rather, theta max is 1 over m squared, theta inverse is m squared. Okay? So we end up getting that, we plug this into Petury, we get delta times 2 to the m squared, and we get that delta then to, cancel out this exponential growth needs to be something on the order of 1 over 2 to the m cubed. Okay? So that's actually how precise these original results were. We wanted 1 over 2 to the n to match the Hilbert space dimension, and what we actually had was 1 over 2 to the m cubed. Okay? We have 13 minutes. I'm going to take all of them. I'm going to try to improve this, but I'll give you the idea. So this is we're now we went from 2018 to 2019. Now we're at 2021. So here's what we prove. So hopefully I've convinced you so far that the reason that we were sort of stuck with our imprecision, the reason we couldn't improve it very much, had to do with the fact that we were using Lagrange extrapolation. That was setting this parameter I was calling theta max, which was then dictating this poor scaling in terms of the robustness. And so what we need to improve, and we're sort of aware of this for a long time, is sort of a more error-robust means of polynomial extrapolation. Some way in which we could sort of tolerate some errors. We weren't just trying to do this sort of union-bound game where we were just saying, basically we can ignore the errors because the success probability is so high. We needed to do better than that. And so we're going to do this by oversampling. In other words, taking many more points than the degree. So far, using Lagrange extrapolation, we only needed like, if the degree of the polynomial was like 2m, we needed like, around 2m points, right? We're actually going to exploit the fact that we can take many, many more points, right? That just corresponds to many more of these correlated circuits. And so here's what we prove. So we prove the following theorem, and I'm not going to prove this. You can look it up. But we call this the robust Berlekamp-Welsch theorem. And it says the following. Suppose we have d squared faulty evaluation points, which I'll call theta I, yi, to a polynomial p of theta of degree d with the property that first, all of these points are in this narrow window 0 through 1 over d. And two, we know that at least 2/3 of these points, yi, the evaluation points, are delta close to the polynomial. Okay? Very similar to what we were talking about before. Okay? Well then, here's what our theorem says. Suppose I give you a polynomial, any polynomial, q of theta, and I say that this polynomial is delta close to 2/3 of the points. But it could be 2/3 of the points that's very different than what p is close to. Some other 2/3 of the points are delta close. That's all I know about q. And no matter what q is, if I look at this tiny interval of 0 through 1 over d, q has to be delta times 2 to the d close to p. Okay, so is the setting clear? So I have these points, and I know that 2/3 of them are delta close to p. And now I'm saying, suppose someone gives you another polynomial q. It's not p, not necessarily p. We'd love if it is, but it may not be. The only thing we know is that q is delta close to a potentially different 2/3 of points. Well then, no matter what q we were given, they have to be pretty close on this narrow subinterval. Okay? What is pretty close? Like delta to the 2 to the d. Okay? Any ideas how are we going to get this polynomial q? I've been cagey. This is a mathematical theorem. It's an information theoretic. It doesn't actually say there's an algorithm that comes up with the polynomial q. So what are we going to do? Any ideas? Good. No, we don't, but we could. That's not how we do it, though. Oh, these are all really good ideas, but we were thinking about something much more stupid than this. These are all very good ideas, but no. Here's what we're going to do. This is just a mathematical statement about polynomials. We're going to use the fact that if you remember way back to the Stockmeyer algorithm, the Stockmeyer algorithm was talking about an NP oracle. So we're already using an NP oracle in this algorithm, right? So we're actually just going to ask the NP oracle, right, to give us this polynomial q. That's it. It's going to give you the polynomial q, and we're okay with that because we're already using an NP oracle somewhere else in the proof. So an NP oracle is fair. But why is this an NP problem? That's the key question. That's not totally obvious. In other words, what is an NP problem? It means that you can check this problem. In other words, some magical being gives you a polynomial. We call it q, right? What do you want to check? You want to check that this polynomial is close to these points, on 2/3 of the points. What do? Yeah, you just plug it in. That's it. You just take all of the points. You take what the NP oracle gives you, q. Just make sure it's delta close on 2/3 of the points. The whole reason we're using this theorem is because it doesn't matter which 2/3 of the points are correct. As long as any 2/3 are correct, this theorem holds. Okay? And this allows us to take delta max to be larger, which then allows us to get better robustness. Let me try to say why. Maybe that's the last thing I'll say before taking some questions. Okay, so remember what the setting is. We're given these inputs. These are faulty evaluation points to a polynomial p of theta, right? What does faulty mean? It means 2/3 of these points are guaranteed to be delta close to the value of p. Okay? Now, we're going to ask our NP oracle, right? Please give me the polynomial q that's delta close to some 2/3 of these points. Now, we don't have the ability to check that what the NP oracle gave us, corresponds to P. We don't. We have no idea. But we can use this theorem we call the robust Berlekamp-Welsch theorem, which says that no matter what polynomial the NP oracle gives us, right, within this narrow subinterval, which is now 0 through 1 over m, because m is essentially the degree, right, these two polynomials have to be somewhat close. That's what our theorem said. Right? They have to be delta, I call delta prime, which is just delta, the original imprecision, times 2 to the degree, which is m. Okay, cool. Now we can plug in Paturi. Right? Paturi is, remember, telling us if you have a polynomial that's sort of bounded on a subinterval, like 0 through 1 over m, how close is it all the way at 1? Now we see that we have an advantage. Why is that? Well, because essentially delta now is 1 over m. Right? Not that delta. Theta max. Right? So 1 over theta max is m, whereas before it was m squared. Okay? The degree stays the same. We get, this is just plug and chug, we get delta times 2 to the m squared. That means we can now take delta to be 1 over 2 to the m squared, whereas before it was 1 over 2 to the m cubed. That's the last thing before I do. Yes?
So before when you were discussing Lipton's proof, you see where even if the average case device was stable, it would work.
Yes.
That would suggest that like I have 1 minus theta max m, I would take roughly theta max to 1 over m.
Yes.
So why do you have to go through this?
Yes, good. Because okay, that's a great question. It's because it turns out there's a perversity that happens when we're not considering Lagrange extrapolation anymore. We lost Lagrange extrapolation here, and because of that, we couldn't make some of the arguments we had made before.
The error correction.
Error correction. That broke everything. That's why we need this new thing. Right.
And you had to abandon Lagrange extrapolation?
Yes, because we wanted to increase the precision, the imprecision. Right? Right. So these things are all connected. Yeah. Sorry. What other questions? Maybe what I'll say is that we can actually, that's not the latest. The latest, we can actually push this even more to 2 to the minus m log m. And then again, like 3 months ago, someone claimed that they could push it to 2 to the minus m. We have not, my group has not been able to fully reconstruct those claims. We hope they're correct, but I'm not 100% confident. But hold on, but what we want is 2 to the minus n. That would give you the proof of this big theorem in quantum advantage that we've been working on for 10 years. Okay? Yeah?
I was just going to ask, what is the new proof, or like this, like what is the improvement? Where are you squeezing it?
Yeah, well, let's see. It's a really simple trick. Can I have 5 more minutes? Maybe something like that. Okay, so a really simple trick. It's so simple it's even a little confusing that this works. So let me tell you how it works. The idea is the following. So we have exactly the same setup. So I'm just copying what I had from before. We have these faulty evaluation points of a polynomial p of degree d, or m, let's say, right? And we know that 2/3 of these points are close to the delta close to the polynomial when theta I is between 0 and 1 over m. M is again it's the degree. It's really 2m, but whatever. Okay. Cool. Now, here's the trick, and it's sort of amazing how simple this is. The idea is, we were using an NP oracle, so why not use the NP oracle even more, okay? And what we're going to ask the NP oracle for is not quite the polynomial Q that approximates these points, but rather a slightly different polynomial, what I'll call a rescaled polynomial. In other words, we're going to replace the extrapolation variable theta, and we're going to instead sort of replace it with x to the k for some sufficiently large k. We're just rescaling. That's all we're doing, right? And now what we're going to do is ask for this new polynomial, which is actually a polynomial of higher degree in this new variable x. Okay? Or another way of saying it is, rather than giving the NP oracle these points, theta 1, y1, theta 2, y2, whatever, we're going to give the NP oracle the points theta 1 to the 1 over k, y1, theta 2 to the 1 over k, y2, and so on. Okay? And we're going to ask for a polynomial of higher degree, k times higher. Right? Now, why does this help us? It seems like it's such a stupid thing it can't possibly help you. But it does help you. Why? Well, first of all, it hurts you, actually. it increases the degree. That seems like a really bad thing, because remember in the Paturi bound, we had an exponential dependence on the degree. So why are we increasing the degree? That seems like it's like deeply ironic, like that. That's the wrong way to go, right? Well, the reason is because if you think about what it's doing, it's sort of this powering, this going from theta to x to the k, sort of making things larger near the unit interval, near 0, and sort of compressing near 1. So what do I mean by that? Well, if you look at what the new sort of theta max is, if it was 1 over m before, well, now it's 1 over m to the 1 over k, right? That's what it is. That's what we asked of the NP oracle, because we gave it theta 1 to the 1 over k, y1, theta 2 to the 1 over k, and so on. So what it's doing is it's sort of increasing the degree, which is bad, but it's also decreasing the theta inverse max. Okay? And when you plug it into Paturi, what you get is all the way at 1, this polynomial is bounded by delta prime times 2 to the km, because that's the new degree, right? It's now km, times your theta inverse max, which is m to the 1 over k. Okay? Well, now if you set k equal log m, right, we have log m times m, or m times log m, times something that's asymptotically smaller. Okay, we're going to actually throw that away and just put a twiddle over the O. Okay, and so in fact, it turns out we can actually just get rid of this if we had a more fine-tuned analysis. But for now, maybe I can put a twiddle over this O and say m log m. That's actually what gives us our state-of-the-art bounds. Okay. All right, cool. Let me just conclude by saying 2 open directions. So I see the main open question in the theory of quantum advantage is to improve this additive precision to 2 to the minus m, as compared with something like 2 to the minus m that we currently have. Okay, or for boson sampling, for boson sampling, it's this factor of 6 in the exponent. Okay. Now, the interesting thing is that we also think we have matching barriers, which is sort of the sad part of this. So I didn't tell you this so far, but it's a little bit disappointing. So on the one hand, we've been able to improve this dramatically. On the other hand, we think that even removing things like factor of 6 to something like a factor of 3 would already be very difficult, would take very new techniques. That's the state of the art. Let me also say that I haven't even talked about noise. So a lot of what my group does is tries to understand if with physical noise, you have the noise that Google is actually seeing, does any of this still hold up? And the answer is very complicated. We think that in some aspects of this do, some aspects of this don't. It's so complicated, I'm not even going to get into this because I'll be talking about it for another hour easily. But that's another big issue, right? So far, this is the theory. This is not talking about uncorrected noise. So we're very interested in how much of this survives, and did Google's actual experiment with uncorrected noise solve a hard problem? We didn't really talk about this. None of this was about that. This was about the ideal case with no noise. Okay, that's all I wanted to say. I'm happy to take questions.